Hello, everyone, and welcome to the first lecture for single variable real analysis. Now, the goal of this lecture is to introduce the most basic and fundamental components of what we're going to study, and that is the numbers themselves. So the goal today is just to introduce the different sets of numbers. So things like the natural numbers, the integers, the rationals, and the real numbers. And we're going to talk about them in terms of how they're described, so what they are composed of, and the properties that we can assume as the fundamental, as the building blocks to everything else that we're going to use going forward. Another aspect of what we'll do in this lecture is we'll use these axioms, these things that we can take as principles of our number systems, and how we can use those axioms to arrive at a simple proof of what's known as the triangle inequality. So that's all for this lecture, is a relatively light introduction to numbers and just one simple proof so you can get a feel for what we're going to be doing in this class. And there's a reason why the triangle inequality is chosen as the first proof here. Not only is it relatively simple, but you're going to see it's one of the most powerful weapons we have in real analysis. It's going to come up over and over and over and over again as we're proving, say, convergence of sequences or continuity of products of functions or all kinds of other areas. So let's go ahead, let's jump right into it. So the first place that we can start is with the most fundamental of all numbers, or at least number sets. And that is the set n of natural numbers. Now, I'm going to start counting at 1 here. I know some people like to put 0 as the first natural number. For us, it's not going to matter. There's not going to be a big fundamental difference between if you use 0 as the first natural number or 1 as the first natural number, because this is really just an index set. And so since it's infinite in both cases, starting at 0 or starting at 1, it's not going to make a difference for us. Okay, so if you want to use 0 as your first natural number, that's fine with me. Okay, but these are the usual counting numbers. So this is, 1, 2, 3, 4, etc. Up to some n, and then the next element is n plus 1, and this continues on indefinitely. So these are the most fundamental numbers that we work with. These are the ones that you learn right off the bat. You learn to count when you're a small child. That's why we refer to these as the natural or the counting numbers. Okay, now from the natural numbers, we can define the set of integers. And one way that you can sort of find the existence of said integers is if you take a small natural number and subtract a larger natural number from it, and you find that this thing goes below 0, right? If I have $100 in my bank account and I take out 200, well, then I have negative $100, at least in theory or in principle. And that means that we can use the integers to quantify these negative versions of the natural numbers. And so in this case, you have 0 sort of sitting in the middle. You think of 0 as being the middle of the number line here, plus or minus 1, plus or minus 2, plus or minus 3, and so on and so forth. And we can actually write this nice and compact. And we could say that this is plus or minus n for every single n in the natural numbers. So that's what the E stands for here. It means an element of. So n is an element of the natural numbers, or, so we have a union, or 0. Sorry. And again, this is the set of integers. Okay, so then we said that there's a sort of a intuitive way of getting the integers from the natural numbers, and that sort of comes from subtraction. Now, we're not going to go too far into this sort of algebraic construction of these things. I just want you to intuit these. But then, if you think of multiplication and division, well, if you multiply two integers together, you again get an integer. But if you divide two integers, you don't necessarily get an integer, right? So 1 divided by 8, that is not an integer. And this naturally leads to the set of what are called rational numbers. And these things are denoted by the set Q. Q stands for quotient. Quotient is just a fraction. And this is P over Q, where P and Q are both elements of the integers. So that's, again, P, Q, E means elements or inside of the set of integers, such that Q does not equal to 0. Of course, we don't want to divide by 0 here. And this is the set of rational numbers. Now, you know that there is much more than just the rational numbers when we're talking about the number line. There are numbers like pi or the square root of 2, which are certainly not in the rational numbers, but are very much interesting numbers themselves. And these things are, or they belong to the set of what's called the real numbers. So that is this R here. So real numbers. Now, I don't have for you an explicit way of saying, R is equal to the set of blah, 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 just like I did above. What we're going to see in a few lectures from now is that you can actually construct the real numbers by sequences of rational numbers. But for now, we are just going to use, what we already understand about real numbers. So you know that things like pi or the square root of 2 or E, these things are irrational numbers. They don't belong to the set of rational numbers, but they do exist as numbers. They are real numbers, right? They exist. So for now, we're just going to use the set of real numbers as R until we actually construct them explicitly in a few lectures from now. Now, here's what I'd like to do. I would like to give you the fundamental axioms that we are going to assume for both the rational numbers and the real numbers. So let me start here with a definition. And this is called an Archimedean ordered field. So let's put it in red since it's a definition. So an Archimedean ordered field. So this is going to be denoted by F. There are lots of choices for these Archimedean ordered fields. In our case, it's going to be either the rational numbers or the real numbers. We're not going to delve into the algebraic construction or definition of these things too much. I just want you to know that these are things we can take advantage of, these properties of Archimedean ordered fields, when we are doing analysis on the real numbers or the rational numbers. So let me list off the properties that these things share, and then we'll talk about them as we go through. So this thing is a set with two operations. So it's a collection of elements, a set, with two operations called addition and multiplication. Okay, so we're starting off very, very abstract, very, very low level, and multiplication. Again, if you're thinking of just the real numbers, well, this is your usual addition and multiplication. But if you've ever taken a group theory course, you know that you can abstract these things in certain ways. Now, we're not going to do that in this class, but it is important to present this in its full generality. Okay, so there is, and let's put this in green, an order relation. So an order relation. Again, you're thinking of the real numbers, you're saying something is bigger or smaller than something else. So this is denoted by A is less than B. And these satisfy the properties, the following properties. So let's list them out. Many of them you already know. They're probably so simple that you don't think about them. But again, as mathematicians, we generalize everything. So if you take an algebra class or a group theory class, you will see that these things can be weakened, they can be strengthened, they can be abstracted in all kinds of different ways. But again, just keep that example of the real numbers in your head while we're going through this. So we have closure. Now, what does it mean? Well, it says that if we take two elements of the field, A and B, belonging to F, then if we add them together, this belongs to F. And if we multiply them together, this also belongs to F. So it's important while we're going through this, you should think about which of these sets of numbers actually satisfy these properties and which ones they fail on. I said there's only two Archimedean fields that we are going to deal with here. That's the rational numbers and the real numbers. So eventually the natural numbers have to drop off, right? And same thing, the integers have to drop off. But so far, both the integers and the natural numbers are closed, right? If I add two natural numbers, I again get a natural number. If I multiply two natural numbers, I again get a natural number. So they're all four of these sets of numbers are closed. They satisfy this closure operation. Okay, so the next one is commutativity. So commutativity tells us that the order of operations doesn't matter. So it says if we have A and B in the field, then A plus B is equal to B plus A, and A times B is equal to B times A. Again, all four of our sets satisfy commutativity. If you say 2 times 3, and I say 3 times 2, both of us are going to get 6 here. Same thing, if I say 2 plus 3 and you say 3 plus 2, both of us are going to get 5 here. So the order doesn't matter for this commutativity relation. Okay, let's look at associativity. For associativity, we're going to say if A, B, and C are in our field, so 3 random elements from the field, then A plus B plus C is equal to A plus B plus C. And we have A and then times BC is equal to AB and then times C. So again, if I give you a list of 3 numbers, 1, 2, 3, for example, I say add them up. Okay, well, I add 1 and 2 first, and then I add 3 on later. So I go 1 plus 2 is 3, and then I get 3 more on there is 6. Or I could take 2 and 3 and add those together first to get 5, and then add 1 more, right? So again, these are things that you understand. We're just giving a proper name to them now. These are things you take for granted on a daily basis with the usual numbers you work with, right? If you're doing some accounting, or if you're checking your bank account or things like that, you're doing this in your head, whether you know it or not. So the next one is distributivity. So this one says that if A, B, and C are in F, then A times B plus C is equal to A times B plus A times C. Again, this is a distributive property. You can add, then multiply, or multiply into each of the elements and then add them together. Again, you know this one, you've seen it before. Okay. Identity. So in this case, we're going to say there exists. Now, there exists elements, we're going to call them 0 and 1. Again, this is completely abstract. Coincidentally, in our case, 0 and 1 actually end up being 0 in the numbers and 1 in the numbers. But again, if you talk to an algebraist or somebody who does group theory or anything that tries to abstract these things away, 1 might be, say, the identity matrix when you're talking about sets of matrices. So these things can be abstracted, but in our case, things are going to line up with what we already understand. So such that 0 plus A is equal to A, and 1 times A is equal to A for all A and F. Now, this is where the definition of the natural numbers comes in, right? Because if you include 0 in your definition of the natural numbers, then it does have this identity element 0. But because I didn't include it, this is one place where the natural numbers do not become an Archimedean ordered field because they don't have that zero element. Now, there's many more places where it fails, so that isn't just what's holding us back here. Okay, let's keep going. Number 6, inverses. This is usually where things start to fail. So let's say if A is an element of your field, then there exists some minus A in F such that if you take minus A and add A to it, you get 0. So this is where the natural numbers fail, right? The natural numbers do not have negative elements. There is no minus 3 to go with 3 to get me 0 back. So what you can think about in terms of constructing number systems is maybe somebody started with the natural numbers, 1, 2, 3, 4, 5, whatever. And they said, okay, but I need these additive inverses. I need minus A's, right? Well, then you sort of naturally get the integers out of this, right? Because you're putting minus 3 into your set as well as 3. And then you can do the same thing with multiplicative inverses to get the rational numbers. So also, for all A not equal to 0, so you need to be able to divide by it, there exists an A inverse, which you write 1 over A in the field, such that A times 1 over A is equal to 1. Again, this is where the integers fail, right? Because the integers, if I have 3, I don't have 1 over 3. So this is what leads naturally to the construction of the rational numbers. And remember, I said the rational numbers are themselves an Archimedean ordered field. So things fail when we talk about inverses. Let's now talk about transitivity. So this is with the order relation. So transitivity says that if A is smaller than B and B is smaller than C, then A is smaller than C, right? So this is a pretty natural one. You know, if I'm 31 and you're watching this, say you're 25 and my dad is 56, well, you are younger than me. I am younger than my dad, and therefore you are younger than my dad as well, right? So this is just the ordering of the real line. The next one talks about preservation of order. So preservation of order, we say that if A is less than B, and if we have another element of the field, then if we add C to both sides, A plus C, this is going to be less than B plus C. So that's just saying, you know, you're currently younger than me, then in 5 years, you're also going to be younger than me, right? So C is equal to 5 in this case. So this is, you know, across the number line, we're saying that, you know, order is sort of preserved. It doesn't matter where you zoom in, right? You can zoom in between 0 and 1 or between 5 and 6. Everything is going to be the same there. Moreover, if C is bigger than 0, then A times C is less than B times C, right? So I'm older than you are. If you double my age and we double your age, then double my age is still going to be bigger. Okay, the next one is a trichotomy. Now, this is something that does not exist in many systems. This is something unique to the real line because it's sort of one-dimensional, if you think of it that way. So we say for all A and B in your field, exactly one of the following is true. Statements is true. 1, A is less than B. 2, A is equal to B, or 3, A is bigger than B. Now, again, think about this in terms of ages, right? You and I, one of the following 3 things is true. I am older, you are older, or we are the same age. This is just that one-dimensional sort of ness of the real numbers, right? That we can always sort of identify who's further to the right on that line. Okay, so everything that I've shown you so far is probably pretty intuitive. You probably use these things on a daily basis. You don't even think about them. You take them for granted, but it's important that we quantify them, right? We should say, right off the onset, what it is that we care about and what properties we can assume while we sort of move forward into real single variable real analysis. Here's the one that you probably didn't think about. And this is called the Archimedean property. You're going to see this quite a bit in the early parts of this class because we're going to use it a lot when we start talking about sequences and particularly convergent sequences. Okay, so this says if epsilon is bigger than 0 and if m is also bigger than 0, then there exists a natural number n such that n times epsilon is bigger than m. Okay, so what does that actually say? If epsilon is bigger than 0, it can be as small or as big as you want, right? It could be 1,000 or it could be 1 over 1,000. Doesn't matter as long as it's a positive number. And you take any other number, we'll call that m. That could be 100 billion for all I care. It says you can add epsilon together enough, and eventually you are going to be bigger than that number, right? That's what this is saying, right? Because you should always think of this as being epsilon plus epsilon plus epsilon, n times, right? That's all that is. So again, you want to think about this in ages. Maybe this is the sort of example we've been carrying through, but think of the oldest person you know, right? That's the M right there. Maybe they're 100 years old. Let's use that, right? Well, I can find enough of my friends that are exactly the same age as me. And if we add all of our ages together, eventually we are going to have a combined age that is larger than the oldest person you know. That's all that this is saying, right? So it looks like a very, very simple statement. It is a very, very simple statement, but it is going to be extremely, extremely, extremely important going forward. Okay, so again, Archimedean ordered fields, the examples here. So examples that we are going to use, well, the field could either be the set of rational numbers or the set of real numbers. So there are many, many other examples of these things. And if you're interested in that, I highly recommend you take a group theory or an algebra class. But for us, this is just a way of talking about the properties that the rationals and the reals have. And like I said, later on in this video series, we're going to see how to construct the real numbers from the rational numbers. It's going to take a little bit of machinery before we get there. Okay, so to close it out, let's get our first introduction to the types of proofs that we're going to see in this class. Now, typically lectures are going to begin with a definition. I'm going to say, we say this about something, and we're going to use that definition and the properties that we already understand about numbers, about sequences, about functions, etc., in order to derive true logical statements from what we already know. So let me show you. Let's say we have a definition here, def. So we define, well, we're going to define the absolute value. Again, you know this one, right? You've seen it. So the absolute value is going to give you the number that you put in back if that number is bigger than or equal to 0, or it's going to give you the negative of that number if a is less than 0. Now, what does this actually mean? Well, let's think of it on the number line for a second. So here's our number line, maybe 0 sitting right in the middle, and I give you 3, right? Well, then the absolute value of 3 is just equal to itself. Now, why do we think about it this way? Well, this is really the distance from 0 up to 3. Similarly, if I give you -4, then the distance from -4 to 0, that is equal to the absolute value of -4, which is 4, right? So distances are always positive. And so what the absolute value function is doing is it tells you how far away from 0 are you? I don't care if you went to the left or to the right. I just want to know how far you got away from the middle of this number line. And again, we're always going to think of 0 as the middle here. Okay, let me present to you a theorem. Now, this is a very, very, very powerful result that we're going to carry with us quite a bit through this class. This is what's called the triangle inequality. So let me give it to you first, and then we will talk about what it says. So theorem, THM, that's just my short form for theorem. It says for all A and B in R, so any two real numbers you can find, if you add them together and ask how far away from 0 they are, so the absolute value of A plus B, this is less than or equal to the absolute value of A plus the absolute value of B. Okay, so how do we interpret this? Why do we call this the triangle inequality? Well, if you've taken a class on vectors, it's easier to intuit this thing with vectors. So if you'll allow me, I'm going to draw this in terms of vectors, even though this is in terms of real numbers. Okay, so I want you to see the geometry of this, even though it's not applicable to our situation. I've got, say, the origin right here. And I've got two vectors. Let's call this one A. And I've got this one, which I call B. Okay, so what this says, if I take A plus B, you remember, if you've taken a class on vectors before, this is adding vectors tip to tail. So we would go across A and then up B. And the result, we'll put it in green, would be this diagonal vector, right? And so you'd say the length of A plus B, we'll just denote that by the absolute value of A plus B. But that also means that the length of A is equal to the absolute value of A, and the length of B is equal to the absolute value of B, just using these things as placeholders so that you can understand what's happening. And it says if you want to walk from the bottom right corner, this big red dot, up to this blue dot, well, the distance, if you travel A plus B, that's going to be a shorter distance than traveling across A and then up B. That's what this is telling you, okay? So you get the same type of thing with the real numbers. It's just harder to draw because it's in sort of one dimension. I think it's much easier to see this. And of course, you can see why we call it the triangle inequality, right? Because it says traversing the hypotenuse of a triangle is shorter than traversing its two sides, you know, one after another. That's where this name, the triangle inequality, comes from. Okay, let's do the proof. Here's going to be our first proof for this class. Now, what I want you to really take note of is the logical steps as we work through this thing. And that's going to go for all proofs in this class, but especially this first one. Here's the first thing. So observe that if I take A, then A has to be less than or equal to its own absolute value, right? Because if it's positive, then it's equal to its absolute value. If it's negative, its absolute value is positive and therefore is bigger than it. Same principle applies to the negative of its absolute value. And you can say the same thing about B. All right, so nothing fancy here. I'm just using the definition of the absolute value. Now, what we can do is we can use the preservation of order for the real numbers, right? The Archimedean ordered field. And so we get that if you add these two inequalities together, you get minus and then the absolute value of A plus the absolute value of B. This is less than or equal to A plus B, which is less than or equal to the absolute value of A plus the absolute value of B. So I added each piece of those inequalities together, leftmost with the leftmost, middle with the middle, rightmost with the rightmost. Now we have two cases here. So let's say case one. The first case is if A plus B is greater than or equal to 0, then its absolute value is just equal to itself. But if I can just draw a little squiggle under here, then this piece is the triangle inequality. Because this tells us, so this implies that the absolute value of A plus B is just equal to A plus B, which from above is the absolute value of A plus the absolute value of B. Good. Triangle inequality works in case one. Let's put a little check mark there so that we can remind ourselves this actually worked. Okay, then case two is if A plus B is less than 0. Again, I get this from the trichotomy, right? It's either greater than 0, less than 0, or equal to 0. Now I dealt with the greater than or equal case, so 2 out of 3 of them in case one. So case two from the trichotomy, the only other case is if this thing is negative. Well, in this case, then absolute value of A plus B is equal to minus A plus B. And so what I get here is this. I can say that the absolute value of A plus B is equal to minus A plus B. Now, let's take a look. I'm going to underline this in blue right here. If I multiply those two pieces by a negative, I will get, so maybe I'll just pull it down here, minus A plus B is less than or equal to the absolute value of A plus the absolute value of B. All right, so I put a negative on this term right here and a negative on this term right here. But because of that, it flips the inequality and it will cancel with that negative right there. And so therefore, I again get my desired triangle inequality here, right? Because if you look at the leftmost piece, the absolute value of A plus B, and the rightmost piece is less than or equal to the absolute value of A plus the absolute value of B. But this is all three possible cases. So therefore, we have covered all possibilities for A plus B, or for the absolute value of A plus B. And so we have proven the theorem. And when we denote a completed proof, we put a little tombstone down in the corner, this little black square. So there's sometimes people put QED, that's perfectly fine as well. There's a few other, I'm just going to use the black tombstone here. Okay, so we got our first taste of proving things in this class, right? We proved an extremely important inequality, which is referred to as the triangle inequality. So you should really think about the geometry there and really think about what it's trying to tell you. The other thing that we saw is the types of numbers that we are going to be interested in this class. And then we got to see, the axioms that we can take for granted, right? What we can assume about these number systems. So we have things like associativity and commutativity. These are things that you're using anyways on a daily basis. But the mathematician in me wants to stress to you that this is not something that we can always take for granted. If you've ever learned matrices before, you know that A times B, with matrices, is not the same as B times A. Similarly, not all matrices are invertible. So that means that you don't have commutativity necessarily, and you don't necessarily have multiplicative inverses. So these things can go wrong, right? Not every set satisfies these things. But for us, we care about the natural numbers, the integers, the rationals, and the real numbers. And everything that we talked about with these Archimedean ordered fields, they hold for the rationals and the reals. So that's something we're going to take advantage of moving through this class.